So we're starting chapter 7, and I want to look at 3 different types of learning mentioned in this chapter: habituation, classical conditioning, and operant conditioning. In this section, we'll be focusing on the first 2. Learning refers to a lasting change in behavior because of experience. That means that in order to learn, we must have memory. Learning can be measured by the amplitude or strength of your learned responses. These are measured in 3 ways: latency, or how long you must wait for the response; degree, or the severity of the response; and probability, the likelihood of occurrence. The amplitude of your responses should increase by learning, meaning that the latency should decrease, the degree should increase, and the probability should increase. But how do we inspire those changes in amplitude? There are a variety of ways to learn. Some learning theorists think that we, along with all organisms, learn by creating associations. For example, we hear the word flower, and shortly after we are met with the image of a flower. Now we can associate the sound of the word flower with its physical form. These theorists argue that the more complex the subject, the more associations we must form. By this principle, we can assume that all organisms, simple or complex, will learn in basically the same sorts of ways. Whether or not this is true, studies based around this concept have yielded important results, as we'll see. The first and possibly simplest form of learning observed is habituation, or the decline in an organism's response to a stimulus once the stimulus has become familiar. A person who moves to the city may find the traffic noises to be loud and obnoxious, but after living among them for an extended period, they will grow used to the sounds of traffic, and they will fade into the background, almost unnoticeable. Habituation is important. We want to pay attention to stimulus to sense danger and protect ourselves, but we can't waste time analyzing every stimulus we encounter. Habituation allows us to focus on unfamiliar stimulus and safely ignore inputs that we have already determined to be inconsequential. Equally important is the opposite, dishabituation, an increase in responding caused by a change in something familiar. For example, a city-goer who is oblivious to the sound of traffic will certainly notice if the noise suddenly stops. Changes in stimuli offer us important information about the world around us. Think about dishabituation in nature. Suddenly, the background noise of birds chirping has ceased because a predator has been detected. This alerts the animals on the forest floor, who can now take measures to protect themselves from a threat they wouldn't have otherwise perceived so soon. These types of learning are important, but they only offer us a little bit of information. Other types of learning are necessary to know more after we've determined whether we need to pay attention to a stimulus or not. These other types of learning offer information about the relationship among events. Some actions cause or prevent certain events. Some behaviors magnify an experience, while some experiences perpetuate certain behaviors. These too can all be thought of in terms of associations. Classical conditioning deals with experiments that produce a conditioned response to arbitrary stimuli, paired with an unconditioned stimulus. One of the earliest experimental examples of this would be the work of Ivan Petrovich Pavlov. In one of his basic experiments, Pavlov observed that a dog would salivate when presented with food, but would not salivate, obviously, to a neutral stimulus like the sound of a bell ringing. Pavlov began to ring a bell just before presenting the dog with food, for several cycles. Finally, when Pavlov rang the bell without presenting any food, he was successful in conditioning the dog to salivate at the sound of a bell, even when there was no food. The dog had created an association between the sound of the bell and the food. Pavlov used specific terms to describe the pattern of his experiment. The first step in the pattern, Pavlov determined, was to define an unconditioned response, or the biologically determined reflex triggered independent of learned behaviors, like the dog salivating when presented with food. The trigger for the unconditioned response, in Pavlov's terms, was an unconditioned stimulus, or the food itself. Next, you should determine the conditioned response triggered by a conditioned stimulus that is initially neutral, in this case, salivation at the sound of a bell. These terms are often abbreviated to UR, US, CR, and CS. This simple type of learning is called Pavlovian conditioning, or classical conditioning, the second type of learning mentioned in Chapter 7. Further research has proven that this sort of learning occurs in a wide array of species and situations. Classical conditioning can be viewed outside the lab in our daily lives as well. An emotional response evoked by a song we associate with a former lover can be attributed to conditioning through our experiences, as well as sexual arousal in response to a neutral word or gesture can be attributed to our conditioning to understand such a term sexually. Some experiments that expand upon the Pavlovian method have produced interesting results as well. In a process called second-order conditioning, we can create associations across multiple objects. For example, once the dog has been conditioned to salivate at the ringing of a bell, we can shine a light every time the bell sounds. Soon, the dog will begin to salivate each time the light is shown without the bell noise, as our test subject has determined a relationship between the light and the bell noise, which we already determined to be associated with food that causes salivation. Luckily, our canine won't salivate every time it hears a bell or sees a light forever on, because conditioning can be undone over time. As the conditioned stimulus is presented again and again without the unconditioned stimulus, the conditioned response will gradually fade until it no longer occurs. This is a process called extinction, or the undoing of a previously learned response so that the response is no longer produced. This is not because the organism forgets the conditioned stimulus, as experiments have shown. Experiments with spontaneous recovery are examples that show this to be the case. This phenomenon is observed in animals that have completed the extinction process and been left alone for a rest interval. After this period, presentation of the conditioned stimulus will elicit the conditioned response despite being fully extinguished earlier. Apparently they remember it, but through the extinction process, they are conditioned to create different associations rather than completely forget those prior. Exposure therapy in humans is very similar to this extinction process. Take, for example, a person who is afraid of dogs. Exposure therapy would work to keep the subject safe and comfortable while showing them images of dogs, and eventually real dogs, until they have overcome their anxiety. However, spontaneous recovery of their anxious biological response is likely to occur if they encounter a strange dog in public. Such a relapse is actually very normal. Associations in our minds are more difficult to break down than you'd have guessed. Unfortunately, in real life, we receive a variety of stimuli that signal the same information despite their differing forms. For example, the side of an apple tree might signal food to a squirrel, but the squirrel must be able to perceive that each apple tree, be it tall or short, will provide that. If we can't recognize stimulus generalization, the associations we learn wouldn't be very useful at all. However, we risk overgeneralizing stimulus. Suppose you assume a defensive position when someone approaches you with an angry facial expression. Thanks to generalization, we can determine anger on very different facial structures. But without the ability to discriminate, we might become defensive toward other facial expressions like sadness, which might hinder our social interactions. We discriminate by responding in a way that's guided by the stimuli in our view. Organisms are very capable of discriminating stimuli, however, and we can even interpret inhibitors, which signal that a certain event is not going to happen, and therefore induce the opposite biological response. Let me explain. If a dog from our earlier experiment hears the bell noise that has been linked to food, represented by CS+, it will likely begin to salivate. If we hit a piano key, the similar noise might also induce salivation because of generalization. But after several times of hearing the piano noise without presentation of food, the dog will be able to discriminate the difference between the bell and the piano noise. The piano noise will become associated with the absence of food, and thus the dog will not salivate. The piano noise has become an inhibitor of salivation, and thus is represented as CS-, signaling that no food is going to come. Interestingly, as we view these conditioned stimuli as signals, we can see that experiments in which the conditioned stimulus is provided simultaneously to the unconditioned stimulus are unsuccessful in producing the conditioned response. In experiments where the conditioned stimulus is provided after the unconditioned stimulus, the results are even worse. From experiments of this nature, we learn that forward pairing, conditioned then unconditioned, is more successful than simultaneous or backward pairing, unconditioned stimulus followed by conditioned stimulus. When we think about these projects in simple terms like this, the conclusion and associations make sense. However, when we look at experiments holistically, things become more complex. For example, there are white fluorescent lights in the lab where our dog is being tested. Who's to say that as a result of the environment, the dog didn't construct an association between the fluorescent lighting of the food in addition to the bell noise. This leads us to a very important question about contiguity and contingency. Is the conditioning a result of the fact that the conditioned and unconditioned stimuli arrive close together chronologically, or because the conditioned stimulus provides information about the unconditioned stimulus's arrival? Experiments show that a conditioned response is acquired only when the conditioned stimulus is informative about things to come. Look at this example. In one trial, a rat experiences periods of time with a bell noise and periods of time without. Regardless of whether the bell sounds, the rat receives an electric shock 40% of the time. At the end of the trial, the rat is offered the stimulus of a bell ringing, but does not display the conditioned response. In the second trial, during periods of the bell ringing, the rat receives an electric shock 40% of the time, but during periods where the bell noise is absent, the rat is only shocked 20% of the time. By the end of his trial, the rat exhibits a conditioned response to the stimulus of the bell noise, because an association has been constructed. The bell now offers information that is useful to the rat, that whenever the bell rings, the chance I will get shocked increases by 20%. Experiments like this provide us with better understanding of the importance of contingency. More experiments show that animals in non-contingent trials, or trials that are random and uninformative, are more stressed and uncomfortable. When given the option, animals will reliably choose to enter situations where there are signals for danger and likewise signals for safety. The animals in non-contingent trials are never able to relax because even though there is no trigger for fearful response, there is no signal of safety. Findings show that animals are more anxious in unpredictable situations. From this, we learn that animals are acutely sensitive to comparisons among probabilities. Animals begin to form expectations that are weak at first and solidify as experiences confirm those expectations. Adjustment of these expectations, whenever a surprise occurs, can also be viewed as a form of learning. Remember very simply like this: when you are surprised with more than you expected, your expectation from the next time goes up. When you are surprised with less than expected, your expectation goes down. When you receive exactly what you expected, there's no change. Surprise is important in how we learn. Look at the blocking effect. When a stimulus does not offer new information and is therefore unsurprising, a conditioned response will not be acquired. Take a look at this example. A rat has been conditioned to associate a hissing noise with a sexually receptive mate, and thus displays the conditioned response of arousal when the hissing noise sounds. In the following trials, the hissing noise is paired with a bright light, and then a sexually receptive mate. One would think that in the third trial, the rat would display a conditioned response to the bright light itself, but it doesn't. The light only provided redundant information to the rat, and therefore it did not attempt to create new associations. This result is called a blocking effect. Now, it might be tempting to assume that the conditioned response will always be the same as the unconditioned response, just as it was in Pavlov's experiment. But in reality, this is rarely the case. Most of the time, the conditioned response is very different. For example, if a bell noise signals an electric shock, the rat will display the conditioned response of becoming alert and tensing in anticipation of the shock, while the unconditioned response to the shock itself would be to jump and escape. Think of these different responses in terms of energy conservation. The conditioned response in this case is parasympathetic, and the unconditioned response is sympathetic. This sort of learning can be very important to animals in nature because they will be better equipped to respond to different stimulus if they are able to prepare for their arrival. Preparation for the unconditioned stimulus may take many forms. Consider the situation of heroin addicts. The potent drug lifts the user's mood and decreases pain, but continued use of the drug will lead to the development of a tolerance. This is partly because of the way our bodies prepare to use the drug when conditioned stimuli are present. At first, the drug will improve a user's mood, for example, but the body must then counter the effects of the drug to stabilize and bring the user's mood back down. After only a few uses, the body will register the sight of a heroin needle as a trigger and will prepare for the drug by countering its effects before the drug is even introduced. Thus, when the drug is injected, its effects will only cancel out the body's preparations, and the user will not be able to receive the full effect of the heroin. Higher and higher doses of heroin will be necessary to maintain the effect, and a dependency has formed because now even the sight of a needle will signal to the body that it needs to counteract the drug, and your sensitivity to pain and your mood will ultimately be much worse than if you had never used the drug at all. Your body's preparations are called a compensatory response, one that offsets the effects of the upcoming unconditioned stimulus.